Hello, welcome to session 17 in the series Analog Circuit Design using ADS. My name is Anurag Nigam and I'm going to continue first with a correction. Okay, and this is a serious correction. This was a mistake, my confusion, and I apologize. What happened was I mentioned something called tau b, and this tau b is not the base transit time. So I just want to make a correction that in the section 16 I was saying that this was a base transit time. It has been a long time and I got confused. So it is not the base transit time. The base transit time is tau f, which I'm going to talk today, while this tau b, okay, is going to be what you call relaxation time, okay, for the minority carriers in the base, right? So now if you increase the relaxation time, right, if you increase relaxation time tau b, okay, which is a recombination, which is to do with the recombination of holes with the electrons, right? So if you increase that time constant, right, then this figure wb square by twice of dn tau b, okay, so this is going to become small, right? And then base transport factor will go close to 1. And another thing is that this hyperbolic nature would become more linear nature if tau b is increased, right? So that's basically base transport factor affected by tau b. So just want to make sure that you keep in your mind that this is not the base transit time. This is the relaxation time, or the time between time between when a hole is injected into the base and uh, before it recombines. So that time is called the relaxation time, right? So the recombination component IB1 would go down with this tau b increasing, right? Because there will be less number of recombinations, so IB1 will go down. Okay, so with that correction, let's proceed with the transistor and look at some of the phenomena, right? So first thing I want to discuss is the characteristics. Okay, so I'm going to talk about small signal characteristic, a small signal model of a BJT, right? So first of all, like in case of MOSFETs, I defined that Vi is smaller than twice of V overdrive. That can be considered a small signal. In case of bipolar, I have to do something similar. So I have IC is equal to QADN Ni square over NAWB, correct? E raised to VBE over VT. Now what I'm going to do is I'm going to do IC plus a small variation IC, which will arise because of variation in VBE, a small signal input, e raised to VBE by plus Vi divided by Vt, correct? Now I will do the following. So e raised to x can be written as 1 plus 1 plus x square by 2 factorial plus x cube by 3 factorial and so on, correct? Now I can do the same over here. I can say IC plus small ic will be equal to QADN Ni square over NAWB, and I'm going to separate the term, right? So I can do VBE by VT and then dot e raised to Vi by Vt, correct? And this term is same as IC, so it will be IC plus a small ic is going to be e raised to Vi by Vt. Now I do expansion of e raised to x, so that can be written as 1 plus Vi by Vt plus Vi by Vt square divided by 2, right? So let's write it here, divided by 2 plus 1 over 6 Vi by Vt cube plus and so on. Now what I'm going to do is I'm going to cancel out IC. So I would be left with IC is equal to IC times of VI by VT. So I'll take VI by VT common here, right? Right? And this will be 1 plus half of okay yeah, so this half of uh, okay, so what I was talking was this is can be written as VI over VT sorry plus 1 by 6 times of VI over VT square plus and so on. Now IC over VT is equal to GM0, which we will derive later on also, and IC over VI is going to be equal to GM. So that means that GM would be equal to GM0, right? 1 plus half of VI by VT plus 1/6 of VI by VT square plus and so on, correct? Now this GM would be approximately equal to GMO when VI is much smaller than VT, and this VT is basically KBT over Q, where T is in temperature in Kelvin and KB is the Boltzmann constant and Q is the charge on an electron at room temperature. So at, let's say, 25 degrees C, this is equal to 25 millivolts roughly. So that means that for a BJT, small signal is when the input voltage amplitude is smaller than 25 millivolt, right? So unlike the MOSFET, where you have a control over what is a large signal or small signal, because through overdrive you have a control. Here we do not have a control over what is a small signal. Anything below 25 millivolts at room temperature would be considered as a small signal. So with this out of the way, let's look at some of the phenomena, right? So now if you remember, we had the base emitter junction was forward biased. So let's represent the base emitter junction here, and the base collector junction is reverse biased, and then we have got a very fine depletion region over here. Sorry. Okay, we have a very fine depletion region over here because this is forward biased diode, right? And then this is heavily doped, so we have some depletion of a reverse bias collector base junction in the base, and most of it is in the collector because collector is lightly doped. Okay, and then let's consider this to be the direction of direction convention for this direction of current is reverse of X. So what do we have here? We have seen that the cause of the collector current is basically this gradient in the base, and this is what I'm representing on y-axis is the carrier concentration, right? And then this carrier concentration on this side is this, sorry, and then I'm going to just repeat it on the top side by just copying this one, copy paste, and I'm going to just move it up to here, and I'm going to copy this again, and then I'm just going to rotate this like this, or maybe extend it like this, maybe, right? And I will put this over here, right? Copy this and paste this. Sorry. And sorry. Okay, so this is the majority carrier density. Okay, so we had something like this, and our concern was this NPX, right? Which NP0 was NPO, so this is x equal to 0, this is x equal to WB. Now what happens is, let's say I have, so the reason for this slope, right, is VBE here, right? Okay, that's fine. Okay, so the reason for this slope is VBE causes NP, the concentration NPX to be NPO e raised to VBE by VT, sorry. So that's basically this height, right? And over here it is 0, and this is because of VCB, okay? So VCB being a large number, a negative number, causes the density to be 0. Now if you keep increasing, so what happens is initially when, so let's say we have given a VBE, so let's try to plot the characteristics. So let's say I have got this axis where I'm going to plot the current, and this axis where I'm going to plot VCE for a given VBE. So we are going to plot here VCE for a given VBE. So for a given VBE. Okay, and this is going to be IC. Okay, so for low values of VBE, right, this quantity is not 0 here. Okay, so this minority carrier is not 0. So you can represent this as a line, which is a dotted line. Let me draw a dotted line. Okay, so basically so we have already applied VBE, but then, okay, so this slope has not reached 0. So there would be a point when you keep increasing VCB, this slope will become 0. So basically I'm starting from here, and at some point this slope will become 0. The minority carrier will become 0, sorry, and this would become, beyond this it will become constant like this, right? So this is what you expect. Sorry. So this is what you're going to expect, okay, beyond a certain point where the minority carrier has become 0 and the current has become constant. But in reality, okay, what is going to happen is, if you keep increasing if you keep increasing VBE, then WB, epitaxial value of WB, okay, so that's not going to be WB anymore, it's going to shift inwards, right? So this will cause what is known as base width modulation. So let me just put it here. That is called base width modulation. Okay, so now effectively WB has gone down. So let's write the value of IC. IC is going to be equal to QADN Ni square over NaWB e raised to VBE by VT. Now notice that this WB has now become WB dash, which is smaller than WB. So this current has to further go up. So I will say that this current has become IC dash. So I will remark this. Okay. So instead of calling this as IC, okay, I will call this as IC. And then whatever is the true value of IC beyond this point is going to do like this, right? So whatever is this value, I will call this as IC dash, right? So basically this is because WB has shrunk, or there is a base width modulation that causes the IC value at this point, the IC value has gone up, correct? Now if I was to okay, so now what I'll do is I will do dou IC by dou VCE. Okay, so dou IC by dou VCE. What I mean by dou IC by dou VCE is okay, so instead of IC, let's say assume IC dash, dou IC dash by dou VBE. So that will be equal to E QADN Ni square over NaWb. So this is what we have, e raised to VBE by VT. Now let's do this with respect to dou WB. That's what going to change, and then multiply it by dou WB by dou VCE, correct? So in this case this will become minus QADN Ni square divided by NaWb square, right? E raised to VBE dou WB by dou VCE, right? Now this would mean, and this is basically 1 over RO. Okay, so now this would be minus QA, so that can be written as IC. Okay, so this is IC divided by WB, dou WB by dou VCE. Okay, so this is basically 1 over RO, so RO can be written as minus WB over IC dou VCE by dou WB. Okay, so this is the output resistance due to base width modulation, right? Now this can also be represented in slightly different way. So if you remember, in case of MOSFETs we were talking about what is called the, so let me draw it this way, what we call the early voltage. So same concept is over here also. So what I'm going to do is I'm going to plot here cases like for different VBE. So I'm going to plot IC dash versus VCE for different VBE, right? So this, let's say, is doing this, and then there is another curve which is slightly lower slope, and so this is a function of IC. Okay, so they are for different VBE. Sorry. Okay, so if I was to extend this, slope, so it is going to meet this axis somewhere here. Similarly, I can do this, they will meet at the same point here, right? And I can also do this, so they meet somewhere over here, correct? And we call this as VA. So this is the early voltage, right? And over here, over here this is what is IC, correct? So this is what is IC. Okay, and this is VCE, current value of VCE, right? So if I consider this triangle and then I consider IC dash, so this is IC dash at certain another VCE, right? Okay, so VCE1, VCE2. Okay, So now what is going to happen is let's ignore this value. Okay, let's ignore this value. So this total thing up to here is VA, right? So I can say IC over VA is the slope, correct? And then I want to find out, okay, I want to find out this incremental value on top of that, because this is what is happening over here, right? So basically, if there was no base width modulation, this will become flat like this, right? Okay, so this additional value over here, this additional value is of interest, right? So in this case, I can always say IC dash. So this should be equal to IC dash divided by VCE plus VA. So that means that IC is equal to IC dash is equal to IC into 1 plus VCE over VA, right? And the slope, which is 1 by R naught, is also equal to IC over VA, correct? Now if I take this equation and this equation and this equation, from this I can conclude, right, VA is equal to early voltage is equal to minus WB dou VCE by dou WB. Now my question is the following, okay, is RO a negative number? No, because dou VCE by dou WB. So VCE increases, WB decreases. So this quantity is a negative number, and then this is a negative number, so RO is a positive number. So don't get confused with that. Here also you can see that RO I am considering as a positive number. I'm ignoring the sign of VA. Okay. So here also VA is a positive number. I'm ignoring the signs in this triangle, which are similar triangles. That's what I have done with the equating the slopes. Okay. So now this basically explains what is the output resistance. Now the output resistance will go up if the slope goes down, right? And how would this slope go down? The slope is a function of, so if WB is large, okay, so if WB is large, so if RO goes up if WB is large, okay, because WB minus WB dash, which is delta WB. This delta WB is a smaller fraction of a large WB. So this RO is going to be large if WB goes up. So if WB goes down, the output resistance is going to go smaller. Okay, so that's the logic. This is same as when there is a long channel MOSFET. Okay, then delta X is much smaller than the total length L. So long channel devices have higher output resistance, right? So it's the same concept here. Now the next thing is, if you do a doping in the base, okay, if Na is large, okay, so if Na is large, then WB dash is going to be small. Okay, so if WB dash is small, then the output resistance change in WB is going to be small too, right? So yeah, so if Na is large, delta WB is going to be small with VCE. Okay, which means that this factor is going to increase because WB is going to be small, delta WB, right? So that means that the output resistance is going to be large. Okay, so things we have concluded is this WB is not in your control. Even the doping of the base is not in your control, right? So things are not in your control over here. right? So you can't do much about it as a designer, right? Only thing which you can do is IC. Okay, so if you bias it at lower current densities, right? So basically RO is IC over VA. So if IC is less, right, then RO is going to be large, right? So if you bias a bipolar transistor to a lower current, then the output resistance is going to be large. That's the only thing which you are going to have here. So this concept is true. Now let's look at, we have seen now what is a small signal. Now let's see some of the, so let's see a small signal model. So let me just construct a model here. Okay, so in the model I am going to have some extrinsic resistance, and I can also have some lead inductance, right? So this is, let's say, RB. Okay, then I am going to have C pi, and then I am going to have a R pi. Okay, so this is going to be R pi. Then I'm going to have C mu, R mu, and then I'm going to have here GM, and then this is VI here over here, or rather you can say VI over here, not there. So let me, it's the same thing, right? So okay, so VI over there, so GM VI is the current over here. Then you have got RO, then you will have C collector to source collector to bulk. Okay, so this will be collector to bulk, CB. Then you are going to have extrinsic collector, RC, and then you are also going to have over here RE, extrinsic, right? So this is your base, this is your collector, this is your emitter. Now in a physical device you can see that there is a sub collector. So let me come here. So let's look at the construction of the device. Of course, so now here the collector is over here, right? So you can assume that there is a resistance between here. Okay, so there is a resistance between here, so this is going to be RC. Then you are also going to have a resistance RE, which is going to be very small, but then you are also going to have this extrinsic resistor RB, right? And then you are going to have CJE between B and E. Okay, between B and E there is going to be a junction capacitance. Okay, that is a diffusion capacitance, not a depletion capacitance, because it is forward biased, right? So diffusion capacitance is because of the, so for example, if you forward bias a diode, right? So when you forward bias, the minority carriers, okay, are going to sweep in, and so basically the majority carriers are going to sweep in and the depletion region is going to vanish. Minority carriers are also going to go up, right? So that's what we have seen in a p-n junction diode, and it takes a diffusion length by the time it decays to the same as the bulk, right? So now if suddenly you want to reverse bias a forward bias diode, what's going to happen? The diode is not going to reverse bias till there are minority carriers in the depletion region. So first you have to drain out the minority carriers from the depletion region before the diode can switch off, right? So minority carriers have to go to zero. So there is a delay of time which causes this charge, okay, to be swapped by the delay. Okay, by that delay time the charge has to be swapped out of the depletion region. Okay, this results in the delay of the signal, which is known as diffusion capacitance. Depletion capacitance is because of the space charge, while the diffusion capacitance is because of the delay in basically vacating out the minority carriers from the junction, right? Okay, So with this clear, there is a CJE. So if you look at here, CJE plus CB is going to be equal to C pi. Now what is this CJE is going to be? Okay, this is going to be IC Q equal to CV, right? Okay, so we have a formula Q equal to CV. So basically C is equal to Q over V, and then there it will be a time, right? So that time which is required to drain. Okay, so that is tau d by the time by the voltage. Okay, IC over VD, okay, which will be VBE. Okay, so IC over VB into tau d, where tau d is the time delay to vacate minority carriers, from the junction, right? So now this would be CJE, okay, charge divided by voltage, right, plus CB. Okay, now this CB is basically to do with the charge in the base. Okay, so if you see the charge in the base, okay, was given by half of base, so it will be QA. Okay, so half of base into height, which is NPO e raised to VBE over VT, right? NPO e raised to VBE over VT, that's the height. Half of base into height, right? Then this is equal to Ni square over Na, right? So let this NPO be there, doesn't matter. Now this is going to be charge in the channel. So delta charge, okay, so delta charge and the current basically, so the delta charge is because of VBE, right? So it will be a VT term over here. Just 1 second. Okay, so this is the charge in the base, and the current IC is equal to QA dN NPO e raised to VBE by VT divided by WB. Okay, so now if I take Q by IC, this is the ratio, then I'll be left with WB square y twice of dN, right? This NPO will also cancel out, right? So this will be the slope. Okay, this for a small signal can also be written as dq, so change because of, so WB square by twice of dN DIC, right? So now I can say dq is basically change in charge due to small signal QH, right, is equal to WB square by twice of dN. So notice this is dq, this is q, and this is q by t. So basically this should be equal to a base transit time tau f. Okay, so now the base transit time is tau f. So this is IC, small signal IC, and if I divide this by VI and this by VI, then I'm left with CB is equal to tau f times of GM, right? So that's my answer here. So now the CB will be equal to, so C pi is equal to uh, IC tau D divided by VBE plus tau F GM. Okay, so this is going to be my input capacitance. So let's write this clear. Sorry, C pi. So this is my input capacitance C pi. Okay, so in this small signal we have got C pi, we have got RO. Okay, so let's look at GM, transconductance GM. So transconductance GM is going to be, sorry, transconductance GM will be given by dou IC by dou VBE, and that's very simple. It's going to be QA dn Ni square over NaWb. Okay, e raised to x. So if I do that, it will be left with e raised to x. So that will be VBE over VT. Okay, and then dou this term, so that will be 1 over VT. So this will be equal to IC over VT, or it can also be written as QIC over KBT. Okay, so this is going to be the transconductance. So here I have also got the transconductance. Now the next question comes is, how much is R pi? Okay, so let's look at what is R pi. A small signal input resistance R pi is going to be VI over IB. I can read this as VI over IC, IC over IB. Okay, so IC over IB is beta, correct? So this would be beta divided, and beta for small signal same as beta 0, divided by GM. Okay, so R pi is going to be, R pi is going to be this. So now I have the input resistance R pi here. So I have this R pi. Now what is going to be the C mu, right? C mu and CB, that's what we want to find, and we want to find R mu. Okay, so VC IC, okay, just 1 second. Okay, so R mu. Okay, so now R mu would be equal to basically dou VCE due to recombination current dou IB 1. Now this can be expanded as dou VCE by dou IC, dou IC by dou IB, dou IB by dou IB1. Okay, so this roughly is a factor 5 to 10, right? And this one IC by IB is going to be beta 0, and IC dou IC by dou VC by dou IC is going to be RO. So then this term would be equal to R mu is equal to 5 to 10 times of beta 0 RO. Okay, so that is going to be R mu, and then C mu is the parasitic capacitance. It will be C mu will be equal to the junction capacitance of collector with the base, right? Collector base junction capacitance. So that will be collector base comes junction capacitance 0 divided by square root of 1 plus VCB divided by xi 0, right, times of the area. So that will be the total capacitance C mu. And similarly you are going to have CB will be collector to body. So if you see here, collector has a very large interface with the body terminal, because there is a sub collector involved, right? So let's go to the construction of the device. Okay, so this is the construction of the device. Now you see that this entire thing is a PN junction, right? And this is junction between collector and a body, right? So this is a huge area. So this output capacitance is going to be large. Let's see that. So CB will be, CB0 divided by, again, 1 plus VCB, which is same, VCE, which would be major component of this is VCB only, by Xi0. Okay, so this would be your output capacitance. So now we have covered this guy, and what we are left with now is the eccentric resistances. Now this is very important. Okay, why it is very important, I'll explain you. Okay, and this is something which every designer should know. When I say emitter periphery, I am really not referring to the area of emitter junction. I'm referring to the parameter of the emitter junction, which is more important than the area. So if I go to the construction, okay, so when I say emitter periphery, right, so what's going to happen is there is a base, right, which is basically distributed, but the real base is over here. The real base is over here, right? So this is the real base, and this is going to be connection to the base. Now the least resistance between base and emitter is going to be to the periphery. So most of the current is going to be crowded on the periphery rather than the area. So this resistance is much smaller than, for example, the resistance to the center of the base. So that means that most of the current is going to be crowded on the parameter of the emitter junction, not the entire area. So what is important is, how do you know the size of a transistor? The size of the transistor, okay, at low current density is, the size of the transistor is the emitter area, okay. But the problem here is, as you go up in power, most of the current is going to be concentrated on the periphery, not to the center. So if I consider a emitter, okay, if I consider emitter, then its area is going to be this emitter length and the width. So the total area, emitter area, is going to be equal to length into width. But the parameter of the emitter is going to be twice of L plus W. Right. Now the thing to understand here, because this has caused a lot of damage in businesses, okay, you cannot expand the width to be twice. So for example, if I do this, and this is W and this is L, and if I say I'm going to make twice of W and half of L, this is the same area as here, but then these two transistors are not the same. The transistor on the right, which is this one, is half the power capability than the transistor on the left one. Why? Because the parameter is now halved, because the major portion of parameter is the length, and if you have half the length, okay, that means that you have half the parameter. So if you think that you can make much smaller transistors, okay, bipolar transistors, by cutting short the length and increasing the width, you are terribly wrong. this has caused a big business to fail when we were doing silicon germanium. Okay, this was the main reason for 7 products to fail when we tried to reduce the die size by reducing the length and twicing the width. Okay, this is IBM has burnt his hand with this. Okay, they try to reduce the die size by lowering the length and broadening the width, and thought that the two areas are the same, so the device is going to deliver same power, and it turned out that it didn't, because the emitter periphery is basically the parameter which is important, not the area. So I hope you got the point, and this was very costly actually. This was very costly to IBM. Okay, so having said that, I am going to stop here. I have covered the small signal model of a BJT, and there are lots of other things when you go to more complex device like a what you call HBTs. And here I'll tell you, there is another fab which basically burnt its hand. It's called TIMIC Germany. Okay, they are using a dual heterojunction bipolar transistor, and they thought that they can just use any kind of germanium profile and cause a heterojunction, double heterojunction, and that failed. On the double heterojunction, the process failed. Okay, there's a stability issue. What happened with the silicon with the germanium on silicon? So you cannot just keep on bumping the germanium profile in the base, and there is something called a critical thickness beyond which there are sufficient relocations, and this causes the beta to fail terribly. So TIMIC Germany burnt its hand on the process by failing the beta on their process. So in that case, TriQuint lost a lot of money. Okay, so this is the reason, why the designers have to be very careful when you are designing. It's very important to know the device, right? So here most of my input has come from two gentlemen, and I would like to mention them. One is Gregory Henderson, and the other person is Mark Doughty, right? And one was both were with IBM, but one was with TriQuint later on. So they are aware of what I'm talking about, but as a designer you have to be careful. Thanks a lot. Thank you.